In the valence bond theory, a molecule is considered to be made up of atoms. Electrons in atoms occupy atomic orbitals. This may or may not be hybridized. If they are hybridized, atomic orbitals from the same atom combine to produce hybrid orbitals which can overlap more effectively with orbitals from other atoms, thus producing stronger bonds. Thus, the atomic orbitals are thought to remain even when the atom is chemically bonded in a molecule. In the molecular orbital theory, the valence electrons are considered to be associated with all the nuclei in the molecule. Thus, the atomic orbitals from different atoms must be combined to produce molecular orbitals. Electrons may be considered either as particles or waves. An electron in an atom may therefore be described as occupying an atomic orbital or by a wave function psi, which is a solution to the Schrödinger wave equation. Electrons in a molecule are said to occupy molecular orbitals. The wave function describing a molecular orbital may be obtained by linear combination of atomic orbitals. Consider two atoms A and B which have atomic orbitals described by the wave functions psi A and psi B. If the electron clouds of these two atoms overlap when the atoms approach, then the wave function for the molecule, that is molecular orbital psi AB, can be obtained by a linear combination of the atomic orbitals, that is psi AB equals to psi A plus psi B. Suppose the atoms A and B are hydrogen atoms, then the wave functions psi A and psi B describe the 1s atomic orbitals on the two atoms. Two combinations of the wave functions psi A and psi B are possible. Number 1, where the signs of the two wave functions are the same, and number 2, where the signs of the two wave functions are different. If one of the wave functions psi A is arbitrarily assigned a positive sign, the other may be either positive or negative. Wave functions which have the same sign may be regarded as waves that are in phase, which when combined add up to give a larger resultant wave. Similarly, wave functions of different signs correspond to waves that are completely out of phase and which cancel each other by destructive interference. The signs positive and negative refer to signs of the wave functions which determine their symmetry and have nothing to do with electrical charges. The two combinations are psi G equals to psi A plus psi B and psi U equals to psi A minus psi B. When a pair of atomic orbitals psi A and psi B combine, they give rise to a pair of molecular orbitals psi G and psi U. The number of molecular orbitals produced must always be equal to the number of atomic orbitals involved. The function psi G leads to increased electron density in between the nuclei and is therefore a bonding molecular orbital. It is lower in energy than the original atomic orbitals. Conversely, psi U results in two lobes of opposite sign cancelling and hence giving zero electron density in between the nuclei. This is an antibonding molecular orbital which is higher in energy. The molecular orbital wave functions are designated as psi G and psi U. G stands for Girard, even, and U for ungirate or odd. G and U refer to the symmetry of the orbital about its center. If the sign of the wave function is unchanged when the orbital is reflected about its center, the orbital is Girard. An alternate method for determining the symmetry of the molecular orbital is to rotate the orbital about the line joining the two nuclei and then about a line perpendicular to this. If the sign of the lobes remain the same, the orbital is Girard, and if the sign changes, the orbital is ungirate. An s orbital may combine with a p orbital provided that the lobes of the p orbital are pointing along the axis joining the nuclei. When the lobes which overlap have the same sign, this results in a bonding molecular orbital with an increased electron density between the nuclei. When the overlapping lobes have opposite signs, and this gives an antibonding MO with a reduced electron density in between the nuclei. In case of pp combinations of orbital, consider first the combination of two p orbitals which both have lobes pointing along the axis joining the nuclei. Both a bonding MO and an antibonding MO are produced. Next, consider the combination of two p orbitals which both have lobes perpendicular to the axis joining the nuclei. Lateral overlap of orbitals will occur, resulting in pi bonding and pi star antibonding molecular orbitals being produced. There are 3 points of difference between these molecular orbitals and the sigma orbitals. For a pi overlap, the lobes of the atomic orbitals are perpendicular to the line joining the nuclei, while for sigma overlap, the lobes point along the line joining the two nuclei. For pi molecular orbitals, psi is 0 along the internuclear line, and consequently, the electron density psi square is also 0. This is in contrast to sigma orbitals. The symmetry of pi molecular orbitals is different from that shown by a sigma orbitals. If the bonding pi molecular orbitals is rotated about the internuclear line, a change in the sign of the lobe occurs. The pi bonding orbitals are therefore ungirate, whereas all sigma bonding molecular orbitals are girate. Conversely, the antibonding pi MO is girate, whilst all sigma antibonding MOs are ungirate. In deciding which atomic orbitals may be combined to form molecular orbitals, 3 rules must be considered. Number 1. The atomic orbitals must be roughly of the same energy. This is important when considering overlap between two different types of atoms. The orbitals must overlap one another as much as possible. This implies that the atoms must be close enough for effective overlap and that the radial distribution functions of the two atoms must be similar at this distance. Number 3. In order to produce bonding and antibonding molecular orbitals, either the symmetry of the two atomic orbitals must remain unchanged when rotated about the internuclear line, or both atomic orbitals must change symmetry in an identical manner. In the same way that each atomic orbital has a particular energy and may be defined by 4 quantum numbers, each molecular orbital has a definite energy and is also defined by 4 quantum numbers. Number 1. The principal quantum number n has the same significance as in atomic orbitals. Number 2. The subsidiary quantum number L also has the same significance as in atomic orbitals. And number 3. The magnetic quantum number of atomic orbitals is replaced by a new quantum number lambda in a diatomic molecule. The line joining the nuclei is taken as a reference direction, and lambda represents the quantization of angular momentum h by 2 pi units with respect to the axis. Lambda takes the same values as m takes for atoms. When lambda equals to 0, the orbitals are symmetrical around the axis and are called sigma orbitals. When lambda equals to plus minus 1, they are called pi orbitals, and when lambda equals to plus minus 2, they are called delta orbitals. The spin quantum number is the same as for atomic orbitals and may have values plus f and minus f. The Pauli exclusion principle states that in a given atom, no two electrons can have all 4 quantum numbers the same. The Pauli principle also applies to molecular orbitals. No two electrons in the same molecule can have all 4 quantum numbers the same. The order of energy of molecular orbitals has been determined mainly from spectroscopic data. In simple homonuclear diatomic molecules, the order is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2px, pi 2py, pi 2pz, pi star 2py, pi star 2pz, sigma star 2px. Note that the 2py atomic orbital gives pi bonding and pi star antibonding molecular orbitals, and the 2pz atomic orbital gives pi bonding and pi star antibonding molecular orbitals. The bonding pi 2py and pi 2pz MOs have exactly same energy and are said to be double degenerate. In a similar way, the antibonding pi star 2py and pi star 2pz molecular orbitals have the same energy and are also doubly degenerate. A similar arrangement of molecular orbitals exists from sigma 3s to sigma star 3px, but the energies are known with less certainty. The energies of the sigma 2p and pi 2p molecular orbitals are very close together. The order of molecular orbitals shown above is correct for oxygen and heavier elements, but for the lighter elements boron, carbon and nitrogen, the pi 2py and pi 2pz are probably lower than sigma 2px. For these atoms, the order is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2py, pi 2pz, sigma 2px, sigma star 2px, then pi star 2py,